All right, hello and welcome to 1.3 part 2. So we are continuing with finding limits. We're going to look today at something called the squeeze theorem, which will help us show a couple of special trigonometry limits that involve sine and cosine. So three ways we've looked at so far that we can find limits. Analytically, which involved using direct substitution. And if that didn't work, we could factor or cancel, rationalize, find a common denominator for those more complicated rational functions. We've also looked at graphing the function. That's also very helpful, tracing values that are close. And then we also did numerically when we started by using tables, so plugging in values that were close. So numerically and graphically are kind of similar. And then analytically was just using our algebra skills. But sometimes when we have special functions like trigonometric functions, those types of strategies might not always work. So we use something called the squeeze theorem. And here is what the squeeze theorem tells us. The squeeze theorem says if you have one function, we're going to call it f of x, you can see by this picture here, you have a function f of x that is in between two other functions. In other words, you have a function that's greater than it, so we'll say g of x in this case, and you have a function that is less than it, which in this case we will say is h of x. So if f of x is sandwiched between those two functions or squeezed in between those two functions, and if we know that the limit of h of x, the lower function, and the limit of g of x, the upper function, are the same, then the limit of f of x exists, and that is also going to have the same value. So this squeeze theorem directly helps us to prove these two special limits. So these are special in the fact that you're going to want to just have them memorized. These are two limits that you will just be expected to know and have memorized. So theorem 1.9, two special trig limits. The limit of sine of x over x as x approaches 0 is always going to be 1. And the limit of 1 minus cosine of x over x as x approaches 0 is always going to be 0. So these are going to be something that you just want to have committed to memory. All right, so what we're going to do first is we're going to attempt to prove the limit of sine of x over x as x approaches 0 is 1. So we've kind of illustrated here the sandwich effect, and since they're trigonometric functions, we're doing it kind of geometrically. So this is a picture of the unit circle. This here is a sector that helps us visualize sine of x over x. And then you have this small triangle right here, and then you have a larger right triangle. So our sector is sandwiched in between the larger triangle and the smaller triangle. So the smaller triangle, if we look at the squeeze theorem, would be our h of x. This larger triangle would be our g of x, and then the f of x in the middle is this sector. Now, just to give you a little background here, so these points that are given here, since it's the unit circle, the radius is always 1, so that's why this point right here is 1, 0. Remember, any coordinate point on the unit circle takes on the coordinates cosine theta, sine theta. X value is cosine theta, y value is sine theta. And then this point right up here, which would correspond with this point right here, is 1 tangent theta, and that's because the x value is 1, and since this is the opposite side and we do tangent is opposite over adjacent, opposite over 1, it would have to be tangent over 1. So that's why this point right here is 1 tan theta. So that gives you a little bit of background on where these values came from. They weren't just pulled out of thin air. They're actually concepts you already have learned and hopefully understand. So let's take a look at each of these parts. So in the middle, we have our sector. The area of a sector is a certain fraction of the circle. So our whole circle is 2 pi. We're doing everything in radians. So our whole circle is 2 pi or 360 degrees, but in radians it's 2 pi. So this is theta radians out of 2 pi times the area of the circle, which would be pi times radius squared, and our radius is 1. So theta radians out of 2 pi times the area of the whole circle. So this fraction of the whole circle. Then over here on the left, we have our big circle, or sorry, our big triangle. Area of a triangle is half the base times the height. So half of 1 times our height, which is tan theta. And then the area of our smaller triangle here is half, again, half the base times the height. So half of our base, which is 1, times our height, which is that y value on the unit circle. You can see here, there's our unit circle. So sine theta is the height. So if we kind of write this out in a little more simplified terms here, we have tan theta over 2. Those pi's cancel, so we're just left with theta over 2 in the middle, and then sine theta over 2. All right, so what we want to do is, right now we don't have this function. We don't have sine theta over theta, because remember that's the function we're trying to prove has that limit equal to 1. So we need to somehow manipulate this statement to get sine theta over theta in the middle, and then see kind of what's going on the outside and see what that limit is equal to. And we're going to want it to be 1, so we'll see if we can get there. All right, so we ended up with this. Theta over 2 is sandwiched in between sine theta over 2 and tan theta over 2. And there's a reason we have this written in this order right now. You'll see down here when we get to this reciprocal of the inequality. So first, what we're going to do, we want to have some form of a rational theta and sine theta in the middle. So we are going to multiply everything by 2 over sine theta, so that we have a theta over a sine theta in the middle. So if we multiply everything by 2 over sine theta, we end up with, let's see, that 2 cancels with that 2. All of these 2's will cancel, and then everything goes over sine theta. So we end up with tan theta over sine theta greater than or equal to theta over sine theta greater than or equal to sine theta over sine theta. Which then we could even simplify a little bit more using, kind of some simplifying here. This would just be equal to 1. And then tan theta over sine theta, well, tangent theta is sine over cosine, all over sine then. So our sines would cancel out. So we'd really be left with just 1 over cosine theta on this left-hand side. So using our quotient identity for tangent, that gives us sine theta over cosine theta over sine theta greater than or equal to theta over sine theta. And I'm just going to simplify this sine over sine to be equal to 1. So then by that, we are left with 1 over cosine theta is greater than or equal to theta over sine theta, excuse me, which is greater than or equal to 1. So this is our quotient identity simplification. Okay, now we do the reciprocal of our inequality. So remember, we want sine theta over theta in the middle, so we are going to do the reciprocal of everything. Now when we do that, we have to turn around our inequality symbols also. So we get cosine theta less than or equal to sine theta over theta less than or equal to, and then the reciprocal of 1 is just 1 over 1. Flip it, you get 1 over 1. All right, now what we're going to do is take the limit of everything. So we're going to take the limit, and we were looking at the limit as x approaches 0. Well, we're dealing in terms of theta right now. So we're going to look at theta approaches 0. Now, if we take the limit as theta approaches 0 of cosine of theta, we can really just say, okay, let's do cosine of 0 because that exists. If we plug 0 into sine theta over theta, well, that's kind of the reason we're doing this, right? We don't know what that is. So the limit as theta approaches 0 of sine theta over theta, we'll just leave that in the middle. And then the limit as theta approaches 0 of 1, well, that's just a constant, so it'll just be 1. Now, if we simplify this, cosine of 0 is actually 1. So as you can see here now, the limit as theta approaches 0 of sine theta over theta is between 1 and 1. So we have proven our squeeze theorem here. So by the squeeze theorem now, since this function is in between, or the limit of this function is in between two of the same values after we found the limit, that means that is what that limit is equal to. So the limit as theta approaches 0 of sine theta over theta equals 1. All right, so that's how we use a squeeze theorem. You may see the squeeze theorem come up on some of your assignments. It won't be as complicated necessarily as having to do a proof like this. You will just have to recognize that if you have, for example, if we go back to the picture, that if you have, a function that you're trying to find the limit of, and you can recognize that it's in between two other known functions that you can find the limit of, then that's how you would get that limit. All right. So this is just a quick overview of the squeeze theorem. Go ahead to the other part of this video to see more to do with these examples in the rest of your notes.